last thing to do is to look at the binomial theorem and how we can use it to find some different relationships that exist between these binomial coefficients. Everything starts with our binomial theorem. Now I've written it there in sum notation. Okay, but if I expand it out, that is of course what it is. If we have to find the value of this particular sum then, if I want to add up all of them, NCK, so a complete row, but you'll notice I'm starting from 1, so not including the first term. As I say, everything starts with the binomial theorem. So I write it down and I compare. Well, what am I looking for? What have I got? How can I make this thing into what I'm looking for? And usually it's via a simple substitution. In this case, if I just made x equal 1, then in the sum I'm going to get 1 to the power of k, which of course is always equal to 1. Therefore I have that sum of NCK. On the left hand side, when I sub 1 in, like 1 plus 1 is 2, that must be 2 to the power of n. But that is of course when it's starting with k equals 0. So any row in Pascal's triangle will always be 2 to the power of n. Well, it's now just a matter then of taking out that k equals 0 term out of the sum. That'll leave me with 1 to n. Subtract that from the other side, and NC0 is of course 1, and we have our result. That's what this particular sum would be equal to. What about if I just want the sum of all the odd ones? There's my binomial theorem. How am I going to just get the odd ones? Well, there's the full expansion. We just saw that if we sub in 1, we'll get 2 to the power of n. But that's all of them. I just want the odd ones. Well, if I sub in -1, that'll create an alternating pattern, because -1 to an even number will be +1, -1 to an odd number would be -1. And on the left-hand side, well, 1 minus 1 is 0. I've now got some simultaneous equations. I can eliminate the odd ones or the even ones, depending on which ones I want. And in this case, I want the odd ones. So if I do a subtraction, I'll end up with this. 2 to the power of n is 2 lots of NC1 plus 2 lots of NC3, and so on. Wow. Divide both sides by 2, and we have what we're looking for. K times NCK. So again, let's start with the binomial theorem. How do I get that to look like what I want? I would like some mathematical operation that would put K in front of NCK. Differentiation will do that. If I differentiate both sides then, so on the left-hand side, I have to use my chain rule, bring down the power, lower the power, 50th side. On the right-hand side, I'd bring the K down, x will be to the power of k minus 1. But now if I substitute x equals 1 in, and again, 1 to the power of anything is 1, on the right-hand side, I have what I want. Therefore, when I do the substitute on the left-hand side, I'll end up with n to the power of n minus 1. Okay, but you'll also notice the one that we're looking for was from 1 to n, not 0 to n, although in this case it didn't really matter. Because when I take that out, it's going to be 0 anyway, because it's got 0 times NC0. But there's the one we're looking for. So 1 to n actually is the same as 0 to n, but n times 2 to the power of n minus 1. It'll give us a bit of a hint of what to do to prove this relationship. We're going to equate the coefficients of x to the power of n on both sides. Start with our binomial theorem. Now that's what I've got expanded out. And on the left-hand side, I'm going to multiply that by itself. Well, I'm just interested in the terms that are going to produce x to the power of n. So I've got that whole row times itself, what will produce x to the power of n? Well, the NC0 would be multiplied by the NCn, x to the n. And the NC1 would be multiplied by the NCn minus 1. NC2 with the NCn minus 2, and so on and so on and so on. And we could keep pairing them up like that. There's my coefficient of x to the power of n. But I can tidy that up, because remember we know about symmetry. And NC0 is the same as NCn. And NC1 would be the same as NCn minus 1, and so on and so on. And that will create the squares that we're looking for in what we're trying to prove. Okay, so I have one part of what we're trying to prove. I've got the k equals 0 to n of nck squared. Let's have a look at the other side. X to the power of n in 1 plus x to the power of 2n. Well, That's just our binomial expansion. We're looking for the term that has x to the power of n, which would be somewhere in the middle. It would have a binomial coefficient of 2ncn. There it is, right there. Okay, they're the same, therefore the coefficients are the same. Now let's work out what this 2ncn is. Well, that would be 2n factorial, and be careful how you write that. Notice I put it in parentheses, because if I don't, it would look like I'm saying 2 times n factorial. The parentheses are important there. On the bottom we would have n factorial times n factorial, which is n factorial squared, and there's the relationship that we were trying to prove. Let's have a look at an HSC one. So 2020, very similar. In fact, that's basically what we just did in our last example. So we go and show 2ncn was equal to all of those squared. That was the first part of the question. But then they turned it into something quite interesting. They turned it into a perms and coms question. We've got a club has got 2n members, n women, n men. So each group will consist of an even number of members then. So 0, 2, 4. Well, could you call 0 members a group? But anyway, that's what they put in the question. 0, 2, 4 up to 2n. And always having an equal number of men and women. Show, giving reasons, that the number of ways of doing that is 2ncn. If I was just going to choose a group of k men from the n men, then that would be nck ways of doing it. And similarly, if I choose the k women, because I've got to choose the same amount from that group of n women, that would also be nck. Therefore, the number of ways of choosing k men from the group of n men and k women from the group of n women, I would multiply those together. There's the nck squared. But of course, I would do that for every size group. So this, from k equals 0 to n, and that is 2ncn. Now part C, from those groups that we've just chosen, one of the men and one of the women are going to be selected as leaders. Show this particular expression now. There's the number of ways we can do that. So the number of ways of choosing the leaders. We have got our group. So that's going to be nck squared. We've chosen the men and the women. We now have to choose the leaders. Well, there were k men that we selected and there were k women that we selected. So therefore I would multiply it by the number of ways I could choose the leaders from the men and the number of ways I could choose the leaders from the women. K times k, and then summing it up for all the possible size of the groups. K equals 1 to n, k squared, nck squared. Note, I didn't put k equals 0 in there because it's not a group. If you haven't got a group, how on earth are you going to choose a leader from nobody? You can't do that. So it's just k equals 1 to n on that, and there's our expression. Okay, but now we're going to reverse that process. Got to get the leaders first, then choose the group. Okay, find an expression for that one. So if I choose the leaders first, then I've got all n men or all n women to choose from. But now I have to complete the group. I've chosen the leader. That leaves me n minus 1 to choose from, but now I only need k minus 1 from that. That would give me my group of k. That would be n minus 1 c k minus 1. Well, that's for the men, which of course means it's the same for the women, similar to what we saw before. Taking into account all the different size groups we could have, that sum would be n squared n minus 1 k minus 1 squared. Expanding that out to make it clear what we're talking about. And I've factorised the n squared out, but going back to what we proved before, we can say, well, hang on, this is the same as 2n minus 1 c n minus 1. And I just played around with that and made it 2n minus 2 on the top there, and there's the expression. So 15D is playing around with these binomial coefficients, using the binomial theorem to prove things.